in our research seminar. As you can see, it will be given by Romuald Prion, which I haven't seen for 9 months maybe, because he did his diploma thesis with Andre Glatzer at Carnegie Mellon. So I'm really looking forward to what we have done in the past months. Please.
So welcome. At this point I would like to emphasize, if you have any questions, feel free to ask. So today I'm going to speak about hybrid systems, and more precisely how to use Theorem provers as preprocessors for hybrid system model checking. So what are hybrid systems? What are Theorem provers? And what is model checking? So first of all, what are hybrid systems? Hybrid systems are systems that exhibit both continuous and discrete dynamics. So for example, a train controller, flight controller, or many controllers in robotics are controllers that interact with their physical environments. And typically the physical environment is continuous. For example, the velocity, acceleration, position of a train is continuous. Therefore, we have a controller that is typically discrete that interacts with continuous dynamics. So we end up having both continuous and discrete dynamics, and therefore the systems are called hybrid systems. So many of the systems are safety critical. What do we mean by safety critical is that the failure leads to loss of lives and eventually a substantial financial loss. And therefore we like to ensure that such safety critical systems are meeting the design goals. And this is called verification. For verification, we like to ensure that the design goals are met. And there is many ways to do verification. One way is testing. But the problem with testing is it's difficult to make exhaustive. So we end up checking the system for only a subset of inputs. And for that, there is another way of doing verification, and namely formal verification. And what we do in formal verification is we first formalize the system into a model, and based on this model, we prove. So we actually prove that the design goals are met. So even though there could be a discrepancy between the model representing the system and the system itself, such proof still gives a strong statement that the system is meets its design goals. So two ways of doing formal verification is Theorem proving and model checking. But so the first step of formal verification is to formalize the system. For hybrid systems, there are two ways to formalize. The first one are hybrid programs, and the second one hybrid automata. So I'm first going to talk a little bit more about hybrid systems. Then I'm going to present the hybrid program formal system, and then the hybrid automaton formal system. And then I'm going to show how, based on this formal system, we can do formal verification, namely Theorem proving and model checking. Then I'm going to present a work, namely the combining of both Theorem proving and model checking. So what are hybrid systems? As I said before, hybrid systems are systems that exhibit both continuous and discrete dynamics. So typically, we have a controller that is discrete, that interacts with its physical environment, that is continuous. And note that usually the continuous dynamics are expressed as set with differential equations. And we have an interaction between both discrete and continuous dynamics. So for example, let's imagine an object moving in a grid. The grid is partitioned into cells. A cell determines how the object is moving. So here illustrated with the blue arrows, which means that the cell is pushing the object in one of these directions, so in this case to the right. we have a special cell, the forbidden cell, and basically we don't want the object to reach the forbidden cell. So for example, let's take an object with its initial position here, and with an initial velocity towards the upper left part of the grid, and its trajectory is going to look like that. So as we can see, the object is actually reaching the forbidden cell. So one could notice that since it's a trajectory, it should be a line. The trajectory should be a line, but there we can see it's a set of polygons. And it's not a line because actually the tool we use to compute the trajectory is doing our approximations. So therefore it's not a line. We're going to speak about a little bit more about that later. So as I said before, there are two ways to formalize such system. The first one being the hybrid automata. So the idea is that typically a controller is captured with a finite state machine. But in our case, our controller is interacting with its physical environment, with continuous dynamics. So the idea is to extend such finite state machine with a state space that you can see as a set of variables over the reals to capture the continuous dynamics. So we have a finite state machine, a state space representing the physical environment, but we still need to somehow capture the interaction between the continuous and discrete dynamics. And therefore, we append differential equations to the location. That is basically going to represent that depending on the state of the finite state machine, the system behaves differently in regard to the physical environment. Therefore, differential equations over the state space. We also append assignments to the edges to represent that when the finite state machine changes state, that the system may take an asynchrotous discrete change. And then finally we append invariance to both edges and locations to express that depending on the state of the physical environment, the controller behaves differently. Are there any questions? Okay. So for example, the three cells surrounding the forbidden cell can be formalized with this hybrid automaton. So what we do here is we capture every cell with the location, and therefore we set the differential equation of a location to be this differential equation of the cell it represents. And to make sure that the object is following differential equations of the cell it's residing on, we also set the domains of the cells as invariants in the locations. So therefore we have for every cell a location, and to represent that an object can switch cells, we add edges between two locations that represent two cells that are neighbors. So at any given point, if an edge resides within a cell, not in the frontier, then the cell is respecting the invariance of exactly one location, namely the location of the location that represents the cell is residing on, and therefore follows the dynamics of the location that correspond to the dynamics of the cell. And when an object is moving to the frontier, what happens is suddenly the object respects the invariance of two locations. So here we have a choice, and because we have edges between the locations that represents two neighbor cells, the object can switch locations, and that is going to represent a switch of cells. This is the whole navigation instance formalized as one hybrid automaton, so every cell a location and edges between two locations representing two neighbor cells.
What happened about the forbidden cells?
Well, actually, we don't So this is a bit superfluous. We don't really need this location, but to have in mind that every cell is a location, but you're right, it's superfluous. We don't need this location.
Or it should say something forbidden, invariant false.
No, because, I mean, it wouldn't make a difference, because if we invariant is false, then the object is never going to enter this location.
Yeah.
So it would make it superfluous anyways. But it wouldn't express that the forbidden, so the cell is a forbidden cell, and then we want the. We are going to see that later. How to express that we don't want the object to reach the forbidden cell. So the syntax, as we would expect, with a control graph representing the finite state machine. We append the flows to the locations, the differential equation to the locations, the assignments to the edges, and the invariants to both locations and integers. The semantics. For the semantics, we use this set of states. So here with states, we mean both the state of the finite state machine and the state of the physical environment. And we define the semantic with this transitional relation that basically, for a given hybrid automaton, returns the set of all pairs of such states, where the second state represents the state after a run of this hybrid automaton, and the first state represents the state before we run this hybrid automaton. Therefore, the second state is going to be equal to the first state, where after we run the hybrid automaton. So as we would expect, and so here what we do is and with this transitional relation, express that at one step of the hybrid automaton. So such pair of states is in the transitional relation if and only if the second state is equal to the first state after following the differential equation of a location and respecting the invariance of the location, or by following the assignments of an edge and respecting its edge. So here we have expressed one step of the hybrid automaton. So if we want to express that after any run of the hybrid automaton a formula phi holds, we use this formula. So this formula, what this formula basically says is that for any path from start location to an end location in the hybrid automaton, that this formula phi holds at any of these reached end states, end location. So in the case of the navigation instance, we would make phi express the fact that an object is not residing on the forbidden cell. So in the case of the navigation instance, if we show that this formula is valid, where we set phi to express that the object is not on the forbidden cell, then we have shown that the forbidden cell cannot be reached, and therefore we have verified the system. As we said before, yes?
I have a question about, so you said the condition is there exists a function such that, so there exists a function such that, so that's a second order property, right?
Mm-hmm. What do you mean? So there's a function that exists?
It's the existence about the function, so it's a second order logic property.
The
Yes,
second.
so the semantics is not required to be first order.
No, I just,
yes.
of course.
It's a solution to the differential equation.
Yeah.
That's what it is. So,
Yeah.
I'm sorry, I didn't understand your question.
Oh, yeah, you're making an existential statement about a function. There
Yes.
exists a function such that, so this is, want to be sure that this is second order logic.
Is it logic at all?
it's not. It's just semantics.
Yeah, I'm not sure what you mean with second order logic here. Anyway, so this function defines the semantics of this hybrid automata. Alright, so it's defined, it exists, it's for sure. But the question is what this transitional relation is going to look like, right? So what pair of states is going to be in this transitional relation that basically is going to represent the set of steps after running one step of the bread automata.
But I think there's a good reason for your question, because you try to estimate, is this an easy problem or is it difficult? Now, if you see this, you expect this is a difficult question.
Yes, it's a difficult question. Yes, and actually, so a model checker usually tries to show that such a formula is valid. And for example, it's difficult, and actually it's so difficult that it's really difficult to not do our approximations. Right? Did I answer your question? Okay. Yes?
Now coming to the difficulty of solving such problems, do you know of timed automata?
Not exact, but yes, I've heard of it.
So I was just wondering what is still possible doing with timed automata. For instance, if the car would, I was imagining it, the object moving.
Yeah.
If that would be moving at the same speed, whether that then would be sufficient to use a timed automata.
In this case, so I think I didn't mention it, that actually the dynamics are a bit more complicated than that's written on the slides. So actually, we wouldn't be able, as far as I know, timed automata, we wouldn't be able to capture this navigation instance with a timed automata. So as we said, any other questions? So as I said before, there is another way to formalize such hybrid systems, namely the hybrid programs. So here, instead of representing the controller with a finite set machine, we represent the controller as a program. To this program, we add again the state space that is going to represent the state of the physical environment. The program is going to be composed of these follows instructions. The first instruction being the continuous evolution. That is basically representing the system evolving over time by following the differential equation and respecting the invariant of this continuous evolution. Then the assignment instruction, that is representing that the system can have an instantaneous discrete change. And then the sequential composition, that is going to run two programs sequentially. Then the choice instruction, that represents that for two programs, either one of both programs is going to be executed. The repetition instruction, that represents that a program can be executed as many times we want. And then the check instruction, that is basically going to abort the executions that doesn't respect an invariant given by the check instruction. Indeed, yes?
The choice introduces non-determinism?
Yes, I was actually going to say that now. So indeed we have non-determinism, because the choice and repetition instructions so in the choice we have a choice between two programs, so non-determinism. And for the repetition we have the choice of the number of times we execute the program, and therefore non-determinism. And the check, what the check basically does is restrict all these possible executions, the non-deterministic possible executions, to respect the invariants. Any question? Yes?
Yes, this is a check where you abort this execution.
Yes.
After aborting, does the invariant still has to hold, or
no,
can
it
disregard?
can change. It doesn't persist. Okay. It only applies at the moment we run the check. So again, this navigation instance. So here so determines how an object is moving in the grid. We have the continuous evolution instruction that determines how the system behaves over time. Therefore, we use a continuous evolution to represent such a cell. So we set the differential equation of the continuous evolution to be the differential equation of the cell that the continuous evolution represents. And we use the invariant of the continuous evolution to set the domain of the tail to make sure that the object is only going to follow the dynamics of a cell it resides on. So therefore we can capture every cell at the continuous evolution instruction. But we still need to capture the switch that an object can switch cells. and therefore we make a choice over all these continuous evolutions. And to make the choice persistent, we add a repetition to this choice. So what happens here is, if I have an object within a cell and not in the frontier, it's going to respect the invariant of exactly one continuous evolution. When then the object moves to the frontier, and suddenly it respects the invariance of two continuous evolution. So what we can do with the program is we repeat the whole choice, and then with the choice we can go into the other continuous evolution. And therefore we have represented the switching of cells.
Okay, have you explained the syntax of this? I mean, this set union symbol, is that non-deterministic choice or
yes,
or check?
Yes.
Choice or check?
Yes. So this okay. So yes, this basically represents a choice. So we have a choice in this case. So this is a wall navigation sense as a one hybrid program. So we have a choice over all continuous evolution. This is one continuous evolution. Another one. Here the invariant of the continuous evolution, the differential equation of the continuous evolution, and here we repeat the choice over all the continuous evolutions. Are there any questions? Okay. So the syntax, how we would expect a hybrid program is composed either of an assignment, a continuous evolution, a check, a choice, sequential composition, or a repetition. The semantics. We define the semantics with its valuation function that basically for a program returns the set of pairs of states where the second state space of the pair represents the state space after running the program, and the first state space of the pair represents the state space before we run the program. Therefore, the second state space is going to be equal to the first state space after running the program. So as we would expect here, for the assignment, the second state space equals to the first state space after applying the assignments. For the differential equation, the second state space equals to the second state to the first state space after following the differential equation for an arbitrary duration. For the check, check instruction. So what we do here, we don't change state space, so the second state space equals to the first state space, but we restrict. And we do that by ensuring that the first state space respects the invariance set by the check. For the choice instruction, this set equals to the set to the union of the set of the first program and the set of the second program. For the sequential composition, again, as we would expect, the second state space equals to the first state space after running the first program and then running the second program. For the repetition, the second, again, as we would expect, the second state space equals to the first state space where we run an arbitrary number of times the alpha program. So we have now seen two ways to formalize hybrid systems, but we'd like to verify these hybrid systems, and therefore I'm giving you now to present theorem proving, which is one way to do formal verification. Theorem proving is based on the hybrid program formal system. So the idea is to deduce the formula we want to prove using a set of rules and a set of axioms. And because we know this set of rules and axioms to be valid, if we can deduce a formula using these valid rules and axioms, we know that the deduced formula is valid. As an example, let's try to prove this statement so that the positive variable stays positive after incrementing it an arbitrary number of times. We first formalize it into an hybrid program. So x is going to represent the variable. So if x is greater or equal 0, then after incrementing it an arbitrary number of times, then x stays greater or equal 0. So approved.
Let's pause a moment here. What's happening here is you're now using dynamic logic.
Yes.
You didn't tell us.
Oh, okay, so basically,
you know, this is
one of the few universities where really do research in dynamic logic. So, of course, we would like to hear that dynamic logic is mentioned.
Okay, yes. So,
and this, by the way, this is Andre Platzer's contribution. That's his invention,
yes.
Dynamic logic for hybrid systems.
Exactly. So what Andre Platzer, my supervisor at CMU, did is actually to extend the dynamic logic to being able to capture this continuous physical environment and the interaction between the physical environment and the controller. So right now, it's actually a dynamic logic. It's not even, here we don't need specifics for hybrid systems. But as an example, I think it's a good example to see how team proving works.
Yeah.
So we start with the formula that we know to be true, namely if x greater equals 0, then also x plus 1 greater equals 0. Then we use this rule, this assignment rule, to basically replace x plus 1 with x, where we apply an increment, where we increment x one time. Then we use this rule to do induction. So this rule basically says that if a formula holds before executing a program and after executing the program, then this formula is also going to hold after executing the program an arbitrary number of times. Note that these terms here and here make sure that the implication doesn't have other premises or conclusions. Otherwise, this rule will be wrong. So we use this rule to add a repetition to make an induction and add a repetition to the incrementing. The final step is, and I didn't mention it, but the symbol represents an implication. So we use this rule to replace the symbol with an implication. And here we are, we have a formula. So what we have done here is we have deduced the formula from a formula that we know to be true by just applying rules that are true, that are known to be valid. Therefore, our deduced formula is valid, and we have therefore proven this statement. Another way of doing more formal verification is model checking. Model checking is based on the hybrid automata formalization. So the idea here is to let the hybrid automaton run and see the states that are reached. And so what we basically do is we find all the possible paths from start location to an end location in the hybrid automaton. And while we do that, we compute the effects of the differential equation of the locations and the assignments of the edges on the state space. So we compute the reachable state space, the reachable states. So we first start in the start location. We follow the dynamics of the start location, namely the differential equation and the invariant. Then we take any possible edge that goes out of the start location. We follow the assignment of these edges and while respecting the invariant. Then on this location we just reached, we again follow the differential equation set of the sets by these locations. Then again we follow edges, we stay in locations, follow edges, and so on and so on. To make this exhaustive and to make sure we really explore all the reachable states, we do that until no new states are explored. And because eventually we are always going to explore new states, termination is not guaranteed. So usually in model checking, termination is not guaranteed. What's also typical for model checking is our approximation. As I mentioned before, typically the reachable, so the actual reachable states is a subset of what the model checker claims to be the reachable states.
Thus, the model checker needs to know the solutions to the differential equations involved. Is that right?
Yes, it follows. Well, at any point you have to follow. You compute the reachable states. So, for example, if you say in a location, you have your state space, and you follow the differential equation of this state.
You see, some systems are very hard to solve, and some might not have
Yes,
a solution,
I mean,
so you have to keep to simple cases.
Yeah, I mean, of course, even if the differential equations are very complex, then we're lost anyways.
Yeah.
And other questions?
What is the usual restriction? Do you only look at linear differential equations, or
what's it again?
What is the usual restriction on differential equations?
So in this case, typically for model checking, we make sure that the differential equations are linear.
Yes.
Yeah. Because otherwise, as you said, we've mentioned before, it would be too complicated. Yes?
So you're not using any abstraction for the space or to the end. So we are dealing with infinite state model checking. And that's the reason why
No.
It's not misunderstanding.
So basically, the number of states can be infinite.
Yeah, okay.
Does that answer your question? Yes?
For solving differential equations, you use some external software like Mathematica.
Exactly.
Okay, so
As far, I don't exactly know how. So throughout this writing, we are using the model checker SpaceX, and I don't exactly know how they do that. But I would guess that yes, they use something like Mathematica.
And since you're using overhead approximation, you also will typically use some numerical methods on solving them, or
that's also an issue. You have also over approximation on the numerical operations. Yeah. And actually, the team in theorem proving you also need to solve the differential equations, and you also solve. And actually, the Chimera D is we worked with Chimera D, and actually Chimera D is using Mathematica.
yeah, you don't solve the differential equations in the sense that you really get a solution function in most cases, except you restrict your class of differential equations to actually solvable differential equations.
Yeah.
But the other possibility would be use somewhat numerical differential equation solver to get a solution in the sense of which states can be reached.
Yeah. Yes. Yeah. You don't necessarily, as far as I know, you don't necessarily need the solution function. But for theorem proving, you usually solve the differential equation.
Okay.
At least it's what I've seen until now. So throughout this writing, throughout this research, we use the model checker SpaceX. Are there any questions about model checking? So again, so if you remember the trajectory we've shown before of this object moving in the grid, is that we actually computed the trajectory using SpaceX. So SpaceX, after one iteration, says that these states are reached. After some more iteration, that these states are reached. After more iteration, these, and then we finally hit the forbidden cell.
Does it really do this, or does it not go to the boundary of the cell?
It really does that. And this is an about approximation.
Yeah.
So it's really doing that. Yeah. Yeah. Note that the initial velocity is towards the upper left. Yes?
Can you show the trajectory?
Yes?
So, okay, when you go one step, you have this box. Are these the possible states by your head?
Yes.
I would expect that this trajectory becomes bigger and bigger.
It's, yes, you're right. As you can see, well, actually, I wouldn't necessarily. Well,
errors accumulate.
I mean, generally, so what happens is iterative. So you have a approximation. So typically, you can think that the approximation made before are going to lead to new approximations. Does that answer your question?
Yeah, but then the errors accumulate.
What do you mean with
each iteration?
What do you mean with error accumulating?
This line gets wider and wider.
Well, I would suspect. I don't even see that. But I mean, if it's the case, I would expect that yes, that the approximation is getting worse because they accumulate. I would expect that. So the idea is because we have seen that in theorem proving we deduce a formula using a set of rules and axioms, in model checking, we iteratively explore the reachable states. So both approaches are quite different. So an idea here would be to combine both theorem proving and model checking, which is actually what we did. So how do we combine both? Well, so theorem proving is based on changing the structure of the model it's working on. While model checking doesn't do that. It doesn't change the structure of what it's trying to compute the reachable states on. So it seems that intermediate results of model checking doesn't seem to be really helpful for theorem proving, because theorem proving understands changing of structure. So therefore what we do is we first change the model using theorem proving and then run model checking on this modified model. But therefore, because theorem proving is based on hybrid programs and model checking is based on hybrid automata, we need to translate the results of theorem proving into hybrid automata. Therefore, we need a translation from hybrid program to hybrid automata. So we have developed the translation. So let's see the translation for the continuous evolution. So we translate the continuous evolution into automaton composed of a single location, where we set the single location to be the start location and the end location. We set the differential equations and the invariant of this location to be the differential equation and the invariant of the continuous evolution. And well, because the only thing we can do in this automaton is following the differential equation and respecting the invariance, it's exactly what this continuous evolution does. So both automaton and continuous evolution are equivalent. Then, for the assignment, we translated into an automaton composed of two locations. The first location we set as start location. The second location we set as end location. We connect both with an edge. We append the assignment on an edge. And again, here, the only thing we can do on this automaton is follow the edge. And therefore, it's exactly what the assignment instruction does. So both this automaton and this program are equivalent. For the check instruction, similarly, we translate into locations. First location is the start location. The second location is the end location. We connect both locations with an edge. We append the invariant to the edge, and again, because the only thing we can do in this automaton is follow this edge, and therefore follow the invariant, this automaton corresponds to this program, and both are equivalent. Now let's see the sequential composition. So first, what we do is we translate the first program and the second program of the sequential composition into the equivalent hybrid automata. So here we have the automaton corresponding to the alpha program, and here corresponding to the beta program. Then we connect both automata by adding edges from any end location of the first automaton to the second to this start location of the second automaton. And we set the start location of the whole automaton to be the start location of the first automaton, and we set the end locations of the whole automaton to be the end locations of the second automaton. So are both equivalent? So what we're going to do here is we are first going to show that if there's a run in the automaton, then there's a corresponding execution of the sequential composition. And the other way around, if there's an execution of the sequential composition, then there's a corresponding run in the hybrid automaton. With corresponding, we mean that the state reached after the run of the hybrid automaton equals to the state reached after the execution of the program. And because this proof is an induction proof, we assume that these automata are equivalent to the program. So let's assume we have a run of the aberrant automaton. Therefore, we have a path from start location and end location of this automaton. Because the start location is in the first automaton and the end location in the second automaton, at a certain point we need to cross these edges because they are the only edges between the both automaton. And therefore we need to cross this one of these end location of the first automaton, and we need to cross the start location of the second automaton. And because we assume that these automata are equivalent to the hybrid program, to their hybrid programs, this part of the path is going to correspond to an execution of the first program. And the part of this and this part of the path is going to correspond to an execution of the second program. And because the edges we just added doesn't change the state space, we can execute both programs sequentially. And therefore, such a path is going to correspond to an execution of the sequential composition. And in the other way, if we have an execution of the sequential composition, then we have an execution of the first program, and then an execution of the second program. And this is going again to correspond to a path in this automaton, and the execution of the second program is going to correspond to a path in the second automaton. And because these edges we just added again doesn't change the state space, we can glue these two parts together. And therefore, an execution of the sequential composition implies a run in the aberrant automaton. So both are equivalent. So now let's see the choice instruction. So we first translate the first program and the second program into the equivalent automata. Then we add a location, we set a start location of the old automaton. And we add edges from this new start location to the old start locations of the automata. We translate it. And then we set the end location of the old automaton to be the union of both end states of the alpha automaton and the beta automaton. So are both equivalent? Well, again, let's assume we have a run of the aberrant automaton. Therefore, we have a path from start location to one of these end locations. And here we have two choices. Either we follow this edge or we follow this edge. And in this case, if we follow this edge, then the second part of the path is going to correspond to an execution of the first program.
I guess we can cut this short. I mean, we believe it.
What's the name?
It's like composition of finite state machines. So
yes, we believe this. I guess there is more material to come.
Yes.
So we could save time on this.
Okay. So
I also, if now you have iteration, we also believe that iteration can be done.
Okay. So both are equivalent, and for the repetition, we again add the start, and we make the cycle.
Yeah.
So we allow a repetition of these paths, and therefore a repetition of the execution of such a program. So both are again equivalent. We implement this translation based on the model checker SpaceX and on the theorem proved by KMRD, which was developed by Andrew Kratzer. And now, having this translation at the end, the question is, how do we use it? And we have experimented several things, and two things let the model checker terminate on the navigation instance we have seen before, and therefore verify the navigation instance before. Which is interesting because the model checker alone, neither more theorem proving alone, did verify this navigation system, this navigation system we've seen before. So the problem with model checker is that it doesn't terminate. So an idea to combine model checking and theorem proving to make the model checker terminate is to add initial states to the reachable states. So the model checker has less to do, and the model checker is more likely to terminate. So this is our first idea. Unfortunately, the first idea alone doesn't make the model checker terminate. The reason why the model checker doesn't terminate, it's because when when the model checker is in a location, so a cell in the navigation instance, and other approximations are done, and this other approximation in another tails leads to other new approximations. This new approximation leads to other new approximation in the former cell, etc., etc. So continuously our approximations are added, and therefore the model checker doesn't terminate. So the idea is to merge cells together to avoid this back and forth adding of approximations. And indeed, these two ideas combined lead the model checker to terminate. So this is the navigation instance we verified. The blue region denotes the initial position, we set as initial state. As initial velocity, we set a lower and upper boundary. We also merge the cells surrounding the following cells together. And by doing these two operations and running the model checker, it returns this result. So we see that the forbidden state is not reached, and therefore that the navigation instance verified. So what we have done here, we have verified the modified navigation instance, but we still need to show that the verification of the modified navigation instance leads to the verification of the original navigation instance. Therefore, we prove the formula that basically states that if a formula holds after running the habit program of the navigation, of the modified navigation instance, then this formula also holds after running the habit program representing the original navigation instance. The proof is structured by first proving that if an implication of two habit programs holds, then the implication of these two habit programs with the repetition added also holds. And the second formula that we prove, which states that the hyperprogram of the modified navigation instance without repetition implies the habit program of the original navigation instance without repetition. We then combine these two formulas to get our formula that we want to prove. So we prove the first formula by using theorem proving. We first use an axiom to get the first formula. Then we use the unfolding rule to unfold the conclusion. We also use the generation rule to state that we can apply this rule after running the alpha program. We then use the assumption to get the beta program from the alpha program. We then replace the comma in the conclusions with the conjunction, in the premises with the conjunction. We then use the induction rule to add a repetition to the second beta program. We then push the beta repeated program into the conjunction of the conclusion. We then use the conjunction rule to get rid of one of the formula of the conjunction. Note that we use the conjunction rule here in a way that is not foreseen in the calculus introduced by the differential dynamic logic. But we argue that this proof is still valid because two formulas of the if the conjunction holds, then two formulas of the conjunction also holds. And we finally use the unfolding rule again to fold the premise, which leads to the formula we wanted to prove. So we have proven the first part of the proof, and then we prove the second part, again using theorem proving. So we first start by replacing the choice with the conjunction. We then use the rule that states that if a differential equation if the differential equation holds in the continuous evolution, this differential equation also holds in the partition of this continuous evolution. We use that rule to partition the merged cells back into the original cells. This leads to a superfluous cell, namely the cell that covers the forbidden cell. We get rid of the superfluous cell by using this rule. We then finally get our choice back by replacing the conjunction with the choice to finally get the formula we want to prove. These two parts combined leads to the formula we wanted to prove, and therefore the verification of the modified navigation instance leads to the verification of the original navigation instance. The navigation instances we proved are these, where a star denotes an arbitrary direction. Indeed, it turns out that our initial states covers any possible dynamics of these star cells, no matter the direction. Also note that the second navigation instances have slightly easier dynamics. So in conclusion, we developed a translation, implemented this translation. Based on this implementation of the translation, we have proven navigation instances, which is interesting because these navigation instances were not proved before using the model checker alone, nor using theorem proving alone. So this shows potential. This shows potential for the combining of model checking and theorem proving. And an interesting part would be to see other ways of combining theorem proving and model checking. Another interesting thing would be to automatically add reachable states to the initial states, and therefore have a fully automated proof that leverages both theorem proving and model checking. Alright, that's it. Thank you.